Okay, I think we can get started now. Welcome everyone to the last of the V1 Q&A talks. This is the last of four modules that are spec'd out in V1. So, yeah, thanks for joining us on this journey. We have here today with us, oh, geez, we've got a lot of people joining the stage. Whoa, 30 or so people. Okay. Let's see. Hang on. Let me just let everyone know.
I can go to the stage and ask them to join the community channel.
That would be helpful. Thanks. I don't know how they're not seeing a massive list of people in this channel, but anyway. Um, Welcome everyone. We have with us here today Hamza, aka Derans, Otto, aka Varotin, and Benvan, aka Benvan, who will be talking about the peer-to-peer module. Before we get started, I have a couple of things to one thing to call out. So we have the InfoCon is happening in May, and we have a week left for speaker submissions. So if you have any ideas for panels, or you want to hold a workshop, or you want to do a presentation at InfoCon, you need to get your submission in for this idea by next Friday. I am posting the type form for this call for submissions in the community call QA channel, which you'll see above the the voice channels in Discord. Please get your submissions in before next Friday. We are, unlike the other Q&A talks, we are now using this voice channel, and you will this will allow us to have visual aids for the peer-to-peer module. We got some feedback that we would have benefited from visual aids from some of the more technical subjects, so we'll have that today. So without any further ado, I think we can get started. So I'll welcome the speakers to unmute themselves, and yeah, let's dive in.
Okay then. Hello and welcome everybody. Thanks for making it to this P2P Q&A. We'll start off by basically describing how P2P works for the current version of Pocket, and kind of slightly visit what hindrances we've met along the road, and then go and talk more about how we're willing to solve it and kind of improve everything in V1. And I think right after that, we can open the floor for questions. So thanks again for making it. Alrighty, what's a P2P network? I think it's a basic introduction, or let's say a reminder of what a P2P network can be helpful. It's the most decentralized aspect of networking, where everybody gets to talk to everybody without kind of relying on any central entity to achieve that communication. And blockchains in general rely on that to exchange everything that the network or the blockchain needs to keep itself or to maintain itself. For our case, it's a lot of transactions, about relays, about amounts and sends and exchanges that keep being gossiped around, that later on make up blocks that make up all of our blockchain, right? So that's what a P2P network in a nutshell is. For our current version that relies on Tendermint, all of our networking is basically Tendermint's networking, right? And the primary mechanism for communication in that P2P network, or in this P2P network, is random gossip, right? In a random gossip scenario, for me as a peer to tell the rest of the network that I did X amount of work, or that I have heard these transactions being gossiped around, is that I go, as the word indicates, by gossip. I tell everybody I know that I get access to, and they tell everyone else, and it's random until the entirety of the network is covered, right? Now, with this kind of communication, you get some limitations. We're really thankful the network has really grown pretty well and it can maintain itself pretty efficiently, quote unquote. However, beyond a certain level is going to be really unmaintainable primarily because of its randomness in communication. I'm telling everybody, and everybody will tell everybody, imagine how much work is that going to be if you're a million nodes, right? That's almost n squared. So that's one aspect we've been running onto. The other thing is uncontrolled redundancy. Basically, when a node gossips a message, it might receive that message back up to 10 times or 12 times, depending on the size of the network. And these things do not play well when we're trying to scale. If we're aiming to achieve, let's say, well, for the sake of the example, 2 million nodes in our network, receiving that amount of redundancy will not be very beneficial for node runners, not only financially, but also in terms of just, network maintenance and code, and for all the engineers, the endless quest of trying to optimize the network, right? So this in a nutshell, these are the hindrances we've been kind of facing with V0 that we would like to go past. Among other hindrances, of course, I think questions can enlighten more about these aspects we did not mention. Now in V1, we thought to ourselves, we can really simplify this because Pocket inherently does not require a lot of the fancy P2P tooling that's out there. For instance, like when you hear about Karimlia or Chord or whatever, very famous algorithms for P2P, they're pretty much optimized with routing and everything else that allow object lookup. We don't need none of that for P2P. What we need is sufficient communication to allow consensus to do its job and also allow the peers to gossip transactions. Beyond that, we need just a strong relay network, basically. So the thought came that if that's really what it is and you need efficient communication, we can rely on a structured algorithm to control the dissemination of events. And also, as a result, have structured controlled redundancy. That's not gossip. That will simply switch our network from a gossip-oriented P2P network to a broadcast-oriented P2P network. That's when we've came up with something custom to our need that's called rain tree. That is basically a binary tree. Primarily because if you have a random set of data, the fastest way possible to search through that list or structure or set is to go through a binary tree. So we wanted to leverage that to our advantage, primarily because that's fast, but also because our consensus, if you guys have attended to the consensus Q&A, hot stuff does put some requirements to how communication should unfold in a proposing round. So we thought really a binary tree will serve us really nice, except that it's not just a simple binary tree, it's slightly tweaked to reach the performance level we wanted. So I think I'll share my screen here to make this less dry and walk you through how rain tree will help us in V1 achieve what we want in terms of efficient, scalable communication and controlled redundancy that does not overwork the network. So right before I go on, I'm not sure if I can ask you whether you can see the screen, but I'm going to assume you can.
Yep, you can see the screen.
Sweet.
So may have to chain the streams together again. Let me just share my screen as well.
All right. So I'll wait for your green light, Jack, before I continue.
Yep. I love that Discord allows us to have 2 concurrent streams with 50 users, but not one with 100. Very sensible. Anyway, yeah, we're good. I think my stream's live as well.
Sounds good. Probably Discord is having network issues. Maybe they could use Raintree. Never mind, jokes. So Raintree, as I said, will primarily rely on a binary tree structure to disseminate information. What does that mean is that it will have all the participants of the network, the peer list, the infamous neighbor list or address book, be a sorted list, and then it will turn it into a binary tree to achieve its purpose. That is, broadcasting a message, basically, whether that is a block or a transaction. Now, the way it does that is that it first takes that list and kind of puts it onto multi-levels. It turns it into a leveled, height-oriented binary tree with the message originator as the root. And from there on, the rain tree sequence unfolds, such that the originator talks to the right and to the left, according to some math that we'll show you that tells the originator, this is your right, this is your left neighbor. And similarly, every receiving node will act upon a binary tree according to what level it has received the message from. So if we take this example here, we have the fourth level node that is the message originator, and it's about to basically initiate a broadcast sequence to all of the network that will allow the network to receive this block, so to say. So it talks to 3, meaning the nodes to the right and to the left at the level 3, i.e. the next level, and so on and so forth with the second level to the first base level, right? So this way we would have traversed a subsequence or a subset of the network. You would not have talked to everybody, but you would have talked to a substantial amount of nodes, right? There are a few things here to deal with. What happens if... Yeah, go ahead.
Can I just ask a quick question for the previous slide? Is there a reason we're going with 4 levels?
For the time being, for the sake of the example, we're going with 4. But okay, we will show the math behind how you get how many levels you have according to the network peer list you have. But good question nonetheless. This is just for example's sake. Sweet. So with this tree structure, with 4 trying to tell everybody that it has a new block, so for instance, it follows the sequence I've just mentioned, that it goes down the levels it has, talking to right and left. Similarly, all the receiving nodes, depending on their level, will carry down the message to the lowest level possible. Obviously, the nodes at level 1 will not have to do anything with that because they are at the basis or the most basic level, the lowest level that is. There are a few limitations with this design, as you can tell, but also these limitations are inherently what we were looking for because they open space for controlling. We might go through a failure of a node, and the second aspect is that, well, if you just do this, you would not have talked to the entirety of the network. Right? Then what do you do with that? This gives you good space, engineering space, design space. I want to allude to that term specifically. We've had a lot of good conversations about this in the team, and also Luis has tweeted about it. It's pretty important that you open a design space here. With this quote-unquote limitation, so to say, we're able to put in more reliability mechanisms in place. Here we're calling it an adjust resend mechanism, because here's what happens. If 4 sends to 3 and 3 is not able to acknowledge that it has received the message, 4 will assume that it did not receive. That's when it will adjust, basically pick another message, another peer, and resend to it. Except that this time it will not actually wait for the ACK for efficiency purposes and whatnot. So that's one aspect of reliability that's introduced to this binary tree broadcast. The second one is a redundancy layer that will ensure that everybody in the network would have received the message, including the ones that we might have missed due to the lack of any acknowledgement. So the daisy chain cleanup layer, as we're calling it, is when we are at the lowest level, right? The peers at the lowest level here, the one we denoted with ones, have received the messages, and they go on to their neighbors to ask them whether they've received the message or not. in a sequential fashion, allowing to traverse the initial list as in an iteration, but this time only sending the message to the people it does not have, that did not receive it. So the type of message that's being sent around in that level is, I got it, you want it type of message. And this is a good diagram showing how it will unfold. So basically, you got this green node saying, I got this message, 55. Do you want it? One to the left already has it, so it will basically decline, and we would have saved some bandwidth, not send it to that peer. But the other one to the right does not have it. You will send it to it, and so on and so forth. So basically, in a nutshell, this binary tree broadcast style is more reliable when you introduce ACK and add just recent mechanism to it. You have an optional redundancy layer that basically allows you to fill in the gaps of communication that you might have missed, and a daisy chain cleanup layer that makes sure, so to say, that the message has been propagated in all cases. Now, in terms of the math behind picking levels and whatnot, well, slightly changed as of now, but this is a good example. You can pick the top layer by counting, well, the exponents of 3 and then add 1 when it comes to your list. So you take the size of the list and you count the exponents of 3 and you add 1. That's how you get, let's say, 4 levels, or 3 levels, or 5 levels. This is, of course, more updated and cleared up in the spec and in the documentation if you visited that. More about, like, more math to you. This is a good example of how efficient Raintree can be. So, like, with a network of 27 nodes, you get this amount of communications and this amount of ticks. Only with this amount of, with 56 basically acknowledgements, and you can see how it grows with the network growing. And you can see that it's pretty much efficient. From 27 nodes to 177,000, you can see that there's only an increase almost of a factor of 3, from 11 to 27 ticks. And we think that's pretty efficient. I think this is sufficient for... okay, good question. A tick, as in a processor tick in computing, that is the amount, let's say, almost the amount of time to process one instruction by the processor. So that's pretty efficient in terms of time. Alrighty, I think I'm going to stop sharing my screen. This was a quick overview of everything that we've been doing with V1. And I think this is a good time to open up the floor for questions. We've meant to make this quick and painless, but also open the floor for questions to help you get more specific with your questions. So thanks for listening, everybody. Jack, up to you, and maybe let's move on with the questions.
Sounds good. So yeah, if you have any questions, please post them in the community call QA text channel. And you can also request to be unmuted if you want to speak. So if I can, while we wait to see if there's any questions, I just want to take a step back and reiterate the limitations of V0 and how V1 is improving that. So if I understand it correctly, V0 uses random gossip, meaning every node sends, whenever they learn new information, they pass that information along to all the other nodes in the network, regardless of their identity, regardless of whether they need that information or not, which leads to a lot of duplication of information and a lot of bandwidth being used up, and it scales almost n squared. With V1, we're moving towards structured gossip using Raintree. This leads to less message duplication because there's more control over whether the message is actually going to be sent and to who, which will ultimately reduce the bandwidth of the peer-to-peer communication and help us to scale our node count much more efficiently. Does that all check out?
Pretty much, absolutely. A shorter, let's say, description of what you just mentioned is that most of the issues that are coming from V0 have to do with the randomness of gossip. And one important way of quickly resolving that is by giving up the random aspect for a more deterministic structured approach. So pretty much you're on point.
Am I right in saying that we're also going to be, like in some of the other modules, we're also going to be specializing based on the identity of the actors? So non-validators will not be receiving consensus-related gossip, as an example.
Absolutely. The network in V1 will have specific roles, so to say, and specialized nodes. So right now in V0, one of the things we had to pull was to limit the number of validators in the network so that communication can stay efficient and so that not everyone has to be bothered with consensus related messages. In V1, this is going to be further emphasized and kind of the network will be more specialized such that, for instance, full nodes will not be bothered with consensus messages. And I think this is a very important aspect because even in hot stuff, it is very emphasized for the security of the network. That for the security of the network, the validator, let's say ring, has to communicate among themselves and not to have anyone else outside of the ring participate in this conversation. So yes.
And Raintree, is that based on existing? Is Raintree a pre-existing peer-to-peer system that you've seen in use in other projects?
Hard to say. So we have not come across anything like Raintree. So it's pretty much custom and homemade, so to say. However, the approach of traversing through random data using a tree is somewhat classic in computer science. So if we take the example of Karimlia, it's definitely a tree-based structure, except that it's elaborate. It's not per se binary and has buckets and extra logic. With Raintree, you're not really, like, the network is not really a tree. It's a list of nodes. But depending on the position of the node, you will construct a special tree to achieve efficient communication. And that's a really important aspect. It's a very flexible structure that really gets as rigid as it needs to be to achieve a certain purpose and restructures itself. So a shorter answer is no, Raintree is definitely homemade, absolutely 100% organic. and that's one of the reasons why we had to come up with it, is that other structures are very specialized and aimed at a very particular problem to solve. Like Karimlia initially, now it's pretty much used almost everywhere. But it's been conceived for object lookup. Same with chords, same with VKS, and all of the other famous ones. So with a network like Pocket, that is primarily a validator to node type of communication. It's a validator to node type of blockchain. We rather use our own custom solutions.
So V1 will be homebrewed and organic. Nice. Do we have an idea? I'm going to be one of those annoying people and ask you to make a prediction, even though I know you probably don't have an answer. Do we have an idea of how much more scalable this will be than V0?
Absolutely. I mean, I'm not sure if it's going to help to reshare the table we've just showed, but in theory, that is pretty much close to in practice. We can go as high as 177,147 nodes. Well, and still maintain the network and communicate with almost 27 ticks as far as the originator of the message is concerned, and any other one who's propagating. So it's pretty much very scalable.
So does that mean we can go to 127,000 nodes and only see 3 times as much bandwidth requirement as 27 nodes?
Pretty much, yes. Or that pretty much it. That's pretty much it. And that's a pretty strong aspect of Raintree. In addition to the, let's say, propagation time, it will be very much like in worst scenario, it's going to be big annotation event, like a regular iteration. But the short interpretation of this table will be, it will scale. It will scale to 100K nodes, even larger, without any problem. One of the things,
and that's also not taking into account that validators are going to be scaling independently from servicers and so on.
Absolutely, very good addition. This is a very big win for V1 because when you get specialized nodes, you also get specialized communication. And the most important specialized communication we have so far is validators. So servicers will not be participating in P2P as far as the consensus round is concerned. But they will basically broadcast out the transactions they've been making. But it's one way of saying with specialty and specialized communication, you get more performance. One important thing that I think we have to mention here, because part of our research, we've covered very good candidates before we came up with Raintree, is that Raintree performs well no matter the size of the network. Like we can see it goes as high as 100K, but surprisingly enough, we found algorithms that go and perform very well in very big network sizes like 5 million, but they perform poorly in smaller networks because guess what? Dispersion is all over the place and there isn't as many links to keep the network connected. So Raintree will work and will work fine for small networks and large networks.
We have a question related to that from Shane in NodePilot. How many ticks are in V0 with today's 40,000 nodes?
Good question. Otto, do you want to take on that? I can, before I put Otto on the spot, or Benvan for that matter, I'm not sure if we have that data. One aspect that can give you an idea about how inefficient V0 can get at certain times is that message redundancy can go up to 20. So no matter how many ticks, that's 20 of that. That's one way. So Otto, I wonder if you have any data related to that.
It's on that chart showing the growth pattern. Basically, 2 ticks per level is your cost. You can triple the size of the network, and it will cost you two ticks of the clock.
Yeah, but I think V0.
It's a V1.
V1. Was that a V0 question? I'm sorry, did I miss it?
Yeah, the question was how many ticks are in V0 with today's 40,000 nodes? I guess to try and get a sense for like a comparison to today's peer-to-peer bandwidth requirements.
That's a really tough question. Before you get 100% distribution in current, man, that's a lot of ticks. As in, ticks don't, relate to seconds. They're a measurement of a single communication. But we had, I run multiple machines. I've seen machines in the current system be a minute and a half away apart from one another in terms of when they receive that block, right? That's a lot of ticks. You can do a lot of communication in a minute and a half. And a tick is simply as long as it takes to send one message from point A to point B. So it varies. the network's behaving by our standards pretty well these days, but we're talking 2 orders of magnitude less time to traverse the network easily.
Actually, yeah, this question, and as difficult as it is, shows one of the things we wanted to drop with V0. That is, how hard is it to reason about the network, given how random it can operate? Like even in terms of text, you can only speculate, so to say, and maybe measure off of real data, like Sean just showed us. But in V1, at least you have a basic mathematical formula to make you, or to give you the tools to reason about your network and how it will grow in the future, at least to have some near to real world theoretical measurements. So I thought that's pretty important to mention here, and the question really kind of hit hard with it.
Yeah. Also, I want to add like one particular hard thing to do on non-structured networks like gossip networks like we have on V0 right now is to measure exactly how many ticks or even how many connections you were required to get a message to all the parties involved on the network. That's because for this for the network to work, you have to rely on the fact that the networks all are gonna be like gossiping messages, but these messages are not from one source only. Let's say you have consensus message that's fired at the specific times. You have a transaction message that are firing like perpetually on the network, like everyone is sending a transaction to someone or to maybe to claim or approve. So you don't have actual like a baseline to see how this is gonna be affecting you. One special note on that front is like when we drop the validators amount, when we do the validator split, it was obvious like the all pocket nodes started using a bit less of CPU because of the added impact on sending those messages, those consensus message, in the sense that for consensus message that are a specialized type of message that we actually do, we have some requirements of acknowledgement of responding to a specific type of message that you receive, and even you have specific times that the message should go out. On other types of message that are like propagated on the network, like the transactions, you basically do what is called a fire and forget, that you send the message to your peer list and you hope them to do the same as you after they process the message. So like one of the gains on V1 will be like this structured nature of the P2P layer that we are creating right now will benefit like all the, even not even like the consensus one that requires it, but all types of messages that we could have on the P2P layer will be more easy handled by the validators or full nodes for the time being, that will be the ones that will be like in a sense broadcasting and originating messages to one another. So yeah, like one to keep it like in control of what we can do or not, like on a gossip unstructured network like ours, like the amount of peers or participants heavily change what we could like predict or the behavior that we could have.
Thanks for that detail. That really helps. So we have another question here from RSS feed. Is the Raintree protocol currently at a theoretical stage, or has an MVP or a proof of concept been created to validate the theory? Also, how will this be stress tested, especially given that it is homebrew?
So I think Sean can also help us with this question, but the bottom line is that we have Raintree Simulator that shows promising data, and Sean will tell us more about that. It was the courtesy of Sean and Andrew was really helpful to see that data. The second part is that, as you already know, we have a prototype that we're undergoing, and we can see that Raintree is answering to our tests pretty well. So that's a short version of the answer. I wonder if you, Sean, have any numbers from the simulator that we can share.
I don't have numbers right with me. We do have a simulator, and it's simulated like up to 25 layers deep, which is enough for everyone on the planet to run a Pocket node. And we're still in the 40 tick range to get it out. We've simulated with failure rates on the network as high as 35% and still get 100% communication out. We don't really simulate much higher than that, because if your network's more than 30% down, you got big problems. One of the big benefits of Raintree is, even though it doesn't quote route, it works around broken nodes extremely well. We don't. Other protocols call themselves peer-to-peer protocols, and their goal is to simply get two peers talking to each other through the best possible route. Whereas we have a different goal. Our goal is to make sure that every single node gets the message, whether it's a good connection or bad connection, or whether that guy's in Zimbabwe. We need to get him the message, and we need his message to get back to us. So we have good simulations. We do not have real world simulations, no.
And when you said we haven't simulated above 35% because we have bigger problems, are you referring to consensus issues if we have 35% down?
Yes, if you have a 35% consensus failure, you've got basically a stuck chain.
Yep.
So we didn't bother to simulate higher. The structure, the final step in Raintree, also known as the daisy chain cleanup layer, will fix even a massively broken network. It will just take a while. Every node will just walk right and left until it finally finds a pair. So, but even at 35, we're screaming.
Awesome. So we have a couple of questions from Shane here in NodePilot. I was saving them until we got the larger questions out of the way. So first question is, how in V1, how will new nodes seed their chain data? Is there designated seed nodes that new nodes will have to peer with?
Pretty much any, I mean, you can have a seed node, but one of the things about Pocket Network is, we have 35,000 service nodes. And every service node has the blockchain and has the list of 35,000 peers. So you really only need one peer to hand you a list. I believe we're looking protocol-wise at probably asking 3 different people just to make sure that nobody tries to hand you a dirty list or something. And it's important to note that the list does not need to be complete or accurate. It just has to be similar to the state of the network.
There's a very important win that you get with Raintree. It's similar to famously known algorithms. They're labeled one-hop algorithms because they keep the whole network state. But one perk with Raintree is that you don't really keep it. It's out there in the blockchain. But as a continuation of what Sean just said, upon receiving your list, you're going to broadcast using Raintree itself your event of arrival into the network, and everyone else would just proceed to adding you into their list. But yeah, you don't even need a complete list to do that.
A similar question Shane had was, will peering towers be needed in V1 like they are in V0, or is finding good peers in an automated fashion easier in V1?
I don't see any benefit to peering towers under Raintree. You don't, yeah, it just doesn't work the same.
Yeah. So peering towers were conceived to alleviate the stress of peering, apparently, right? You don't have that issue anyway in Raintree. Like peering and seeds, you won't have that stress to begin with. So short answer, nope.
So yeah, that'll make running nodes a little bit easier in V1, which is always great to hear. So we don't have any more questions up here. So we have this might be out of scope of the subject of the call. What could precipitate a 35% consensus failure? Obviously related to what Ben Van was saying earlier.
Pretty big number, but some sort of network disaster. Unrelated per se to the workings of Raintree. Let's assume for a minute that everything works just fine, and then you experience 35% drop in your network. There's going to be a big catastrophe that you'll have to investigate. Maybe, I don't know, we're not that decentralized. Hope not. Or maybe just some internet outage or something like that. For me, at least, how I imagine the network falling down if everything works fine at the code level.
Yeah, this is more of a consensus module question, really, than a peer-to-peer question. So, yeah, we can maybe discuss that topic async, unless you had something you wanted to add, Hamza.
No, not at all. I just had to reread the question. You're pretty much correct.
Okie dokie. Any more peer-to-peer questions? Doesn't look like there are. In which case, we can probably wrap up 10 minutes early. Last chance.
As a reminder, if you're interested in following everything related to Raintree or refreshing or revisiting everything that's been said here, there is a documentation page. There is also published specification in the repository if you go to POC Network GitHub organization. And also you will find in there the Raintree simulator and the ongoing efforts of P2P, including an implementation of a Raintree. So just a reminder, and then we'll always welcome your questions, whether in this call or through Discord or in GitHub.
Yep. Thanks for that, Hamza. I've posted a link to the peer-to-peer V1 explainer, which is just a summary of some of the concepts that we discussed. And then the next link is a more detailed technical specification that the developers are working from. And then, Hamza, do you have a link to the repo with the simulator?
Sure, let me fetch it.
Nice. So yeah, so this is we've got beginner friendly as much as possible, at least explainer, and then a more detailed technical specification and a simulator of entry. So yeah, feel free to dive deep into that and ask any questions you have or provide any feedback, either in the form of GitHub issues, or you can post messages to the V1 research channel, which you'll see listed above the community call QA channel. And yeah, we welcome any participation from the community. V1 is more than just a re-architecture of the protocol stack, but also a re-architecture of how we collaborate with the community. So yeah, we're really keen to get as much involvement from you guys as we can. So if there's no more questions, I think we can wrap up. Please remember, if you have a submission idea for InfraCon for a presentation, panel, or workshop, please submit that by next Friday. That is the hard deadline for submissions because we need to get them prepared. The InfraCon is in a little over a month and a half now, so it's coming fast. And with that said, thanks everyone for joining us today. And yeah, Godspeed on V1. Can't wait.
Woo! Thanks, guys, for attending, and see you soon.
Have a great weekend.